already introduced me. My surname is also a bit complicated, so I can follow up. It's Tuffentsamer. It's even difficult for a German one, so no worry. Yeah, today I want to talk something about Vapour Phase. I can really set up on the presentation of Assembly because we are also not really focused on the pure mass production. We cannot compete with cycle times on the convection oven in most cases, but our strength is flexibility and quality. And I think here we have a very good fit together with Systemtech, and this is also the reason why they have a machine from us. So you see the connection point. Just to follow up what I said, so Vapour Phase is really a technology when you have some complex boards. You see the first one here, where you have high mass components on a PCB together with small ones. And this type of components or PCBAs can be a nightmare to profile on a convection oven. And here we have really the right technology for such applications for the future. So what is Vapour Phase soldering? I hope everybody is familiar with Vapour Phase soldering. It's also a reflow process. So at the end, we are reflowing solder paste, as you know it from the normal convection reflow ovens as well. The only thing what we are doing is, we are using vapor and not air as a heat transfer medium. So again, every time when you have complex or high copper, high masses into your PCBAs, then Vapour Phase should be a technology where you should think about. In addition, as I said, it's flexible, simple, and reliable. I will just jump here. So again, just to summarize the technology, it's a reflow process like the convection oven. We use the vapor for the condensation on the PCBAs, and with the fluid we are using, it's called Galden. That's the liquid we are using to heating up and generating the vapor. It is non-conductive and it's also chemical inert. So it will not react with any material which you have on the PCBA, and it will not destroy any products, parts which you place into the vapor zone. We are flexible in the process temperature we are using. So we have Galdens from 170 degrees process temperature up to 260. So it's really depending which solder paste you have in your production, and we can find the right Galden fluid for your process. So this is really why we call it, it's a flexible process. And then the whole assembly will be transported into the vapor zone, and there is where the soldering is taking place. Here in detail how it's looking like, and this is really in every machine what we are offering. It's the same principle, from the small prototyping batch machines until the big inline machines. Only the transport in the machine looks a bit different, but from the ground principle, basis principle, it's always the same. We have heating plates at the bottom of the process tank, and we have the liquid, the Galden, which is above the heating plate. And then we are generating energy, and this energy can be flexible adjusted, so that's depending on the profile you want to achieve afterwards. But we are heating it up, and what is happening, we are generating a vapor blanket. This vapor blanket has everywhere the same temperature, and we learned it before. We can adjust the temperature by adding the different types of Galden. So this can be 170 degrees if you have really low melting solder paste, or it could be 260 degrees. The normal temperature what we are using for a non-wide vacuum process is 230 degrees, because it's more or less 10 degrees above the melting point, and that is why we're using the 230 degrees. We have a sensor here, and this sensor is very important, because that is our sensor which is signalizing that we can start the process and also that the process is finished. Because once we have the vapor temperature here at the very top of the machine, we can say the machine is ready for production. And now what will happen when we bring the PCBA into the vapor blanket? Due to the cold product which we bring into the vapor blanket will be destroyed. So first of all, the complete vapor blanket will go down, and immediately the vapor is condensing on the PCBA. from that point on, you have zero oxidation on the product itself, without any nitrogen or something, so you need nothing to get the atmosphere oxidation free, because that is really, from the physics perspective, that's the way how it's working. And then we are generating, through the heating plates, we are generating vapor again. So what is happening then? We are heating up, and bringing energy through this liquid film, through the condensation. We bring the energy in the PCBA all over. So it will be on the surface first, but it will go in every part of the PCBA, and therefore you have a very equal and homogeneous heat transfer into the product itself, and also the solder joints, which we obviously want to solder. And then the good thing is, as soon as the product has the temperature, the same temperature as the vapor, so we have this heat transfer into the product, the vapor can go up and reach the sensor again. And this is for us, the trigger that the soldering has taken place. Because now, in this whole chamber, it has the same temperature, and so we can stop the process. If you have very high masses as in the product, then you could add a little bit of extra time just to make sure that this soldering has really taken place. That is what we recommend if you have prototypes which are pretty expensive and you don't want to lose in profiling. Just add a little bit of post-heating time, because overheating is not an issue here. So never ever this product will increase the process temperature which is in the vapor. So for the product itself, it is not a massive problem to be 30 seconds longer in the time over liquidus. So that's actually not an issue at all. And then once this post-heating time is also finalized, then we drive out the hot zone and go into the cooling zone. And then the soldering is done. Again, as a short recap, heating up the process liquid, generating vapor, the transport of the assembly in the vapor, then the heating up of the product, of the assembly with the condensation on it, melting of the solder paste, transport out of the vapor, and cooling of the product. So that are the basic steps which are happening in every vapor phase soldering machine from Asscon. What are the benefits? I told you some of them. So you have zero overheating. Overheating is not possible. You could place 5 minutes, 10 minutes a product in a vapor phase oven, and it would still have maximum 230 degrees, and it cannot be exceeded, because the boiling point, as I said, is the process temperature what we are using. The second one, you have this absolutely 100% oxidation-free process. Oxidation cannot happen in a vapor phase soldering machine. If you have, for example, a post-process, because you want to solder open copper surfaces and they should not oxidate during the cooling process, then of course we can also add some nitrogen in the atmosphere just to avoid oxidation during the cooling process. That is also possible, and this is also optional available. But in the normal process, no oxidation. As I said, we have a very homogeneous heat transfer, so that delta T is below 1 degree at the end of the process. And now I have to add one thing, and this is achievable even with a linear profile. So you don't have to tell your engineers they should profile or to a sophisticated profile on a vapor phase machine. This is actually not necessary. A linear profile is enough. So our old customers, which were the early adopters in a way, they really using 2-3 different profiles on vapor phase machines to solder all their different products. And this is why we say it's a really easy process. And then also coming to the green technology aspect, which is quite important now, the energy consumption of a vapor phase machine is about 30% of a convection oven. So you can save up to 70% of your energy consumption by using vapor phase. And for sure it's a simple and stable process, and with about 2,500 installations worldwide, I think we proved the concept already. Short excursus in the gallium liquid. That is the medium which we are using. It's a perfluoropolyether. It's like a liquid Teflon. As I said, it's chemical inert and it's dielectric, so it's non-conductive. It cannot be contaminated with everything because this fluid cannot chemical react with anything. So it has no shelf life and you don't have to replace it. You just have to fill up the machine once we had a little bit of consumption of gallium, which is the case in the process. So we have a little bit of consumption. The heat transfer is much better than in comparison to air in a convection oven. You can say it's up to 4 times more efficient than transfer the energy by heat. And this is also an important fact, this is non-hazardous. So it has no impact on the labors or something. And also for the environment, it has no bad impact, actually. So here I just briefly jump over, this is what I said already, we have different types of gallium. And for each individual solder paste, we can really find the right gallium with the right process temperature for you. One thing to add, our bigger production machines, so the bigger batch machines and also the inline machines, have also the possibility to terminate the soldering before the boiling point is reached. This is important when you want to use, for example, the normal gallium LS230 with a 230 degrees boiling temperature, process temperature, but you want also to have leaded application on this machine. Then you could teach the machine and say the profile, please terminate the process at 210, 250 degrees as well. And then we follow the measurement standards of the machine and terminate the profile. It is not like we intended to use the technology because we wanted to make it physically safe, but it's also possible to do it. Coming to another aspect which is important when you talk about quality, and this is really closely connected to vapor phase, and this is vacuum soldering. Vacuum soldering is something which is Asscon doing really since the beginning. I think in the second year, so 1997, we invented the first vacuum machine because some space applications make it necessary to reduce the void rates, and that is the reason why we adapted the vacuum technology to the vapor phase technology. Because the normal void ratio, what you can achieve in a normal reflow process, and this is no matter if it's a convection or a vapor phase soldering process, is about 20 to 30%. Less voids is not achievable. Maybe when you put all your engineering inside in solder paste printing, in having the best raw material, in using in your line, then you come a little bit down, but the normal ratio is 20 to 30% in types of watt. When you use the vacuum technology, then I can say below 1% void ratio is possible. And some applications, automotive, space, aerospace, makes it necessary to come down to a really void ratio below 10% actually. That is the requirement what the modern factories and modern manufacturers, OEMs, write in their requirements that below 10% is something that you have to achieve if you are an EMS supplier for those sectors. But it's always depending, the void ratio, it's highly depending on the whole parameters. So it comes from printing, etc., etc. So at the end, we are the last machine in the line. So we have to deal with all the problems which were at the very beginning, but at the end the soldering machine is the machine who brings the final result out of the SMT line. And then the AOE, AOI or the X-ray is really showing the result. Came to the cause of voids. So as I said, it could be air entrapment during printing process of the solder paste. It could also some inclusions of the flux, reactive gases, outgassing of the PCB. If it's a bad quality of the coating of the PCB, then you have gases here, and everything is going as a gas bubble in your solder joint. So at the end, a void is nothing different than gas in a solder joint. So you see a lot of causes. The negative effects, aspects of voids are You have a reduced mechanical stability, for sure, because, yeah, you see, if there is not a solid connection, then you have not the stability where you want to have. You have also a limited heat dissipation. You have reduced stress resistance in the assemblies. You have, for sure, restrictions in the performance when you want to achieve high frequency products or power modules. You want to have the highest efficiency, but with voids this is not possible. And voids is nothing what you can see with an AOI. You can only see it with an X-ray system. But they're there. Yeah, Adrian is helping you. So, and you see some examples now how a normal soldering looks before or without the vacuum process, and how it looks if you do the vacuum treatment afterwards. And you see it's a significantly improvement of the result. So coming from 30% to below 1%. Also here on the LED, you see this massive void here. With vacuum, it's nearly gone. Also here, okay, it's a German, it's a small MOSFET. You see the voids here after the vacuum treatment is nearly gone. And this is nothing what we did artificial, this is really possible to achieve, okay? Coming to how the vacuum process is looking like in our machines, then you see it's not that complicated actually. So I explained the process before, it's always the same. I think I repeat myself. You see, it's always the same. We have the product is going into the vapor, the soldering is executed, the condensation is taking place without oxidation. Once we are in temperature, the vapor is rising. So now the soldering is done, and now the vacuum step is applied. And this is just meant that we have a vacuum chamber above our process tank where the soldering is done. We're driving into the vacuum chamber and close the vacuum chamber with this thermal plate here. And due to that, we can apply the vacuum, because then we have this closed chamber and can apply the vacuum. So you see, afterwards the vacuum is evacuated, and in the vacuum chamber itself, we have also some infrared lighters to keep the solder paste on temperature. Because you have to consider vacuum does only make sense in the liquid stage of the solder paste. So you have to be above liquidus. That is the reason why we are using Galden with a boiling point of 240 degrees, other than the normal lead-free application with 230 degrees. So we are 10 degrees higher because we need the temperature, because the vacuum process takes about 40 seconds in total additionally after the soldering has taken place. Yeah, and then the vacuum chamber is opened again, and the product and the assembly can go to the cooling area again. We are calling it clean vacuum technology. That is Asscon's name for our vacuum technology. Why it is the name? Our vacuum chamber is above the hot zone. So it's out of any contact with the hot vapor, because what is the intention beyond that? It is, we don't want to have maintenance effort on the vacuum chamber. So we want to be a little bit away of the hot zone, so that we have less maintenance on this part of the machine. And every vacuum has a multi-vacuum function. Multi-vacuum means you can apply more than one vacuum step after the soldering, and you could also apply a pre-vacuum. So for example, if you know I have really bad quality in PCBs or products, then you could add a vacuum step before the soldering is taking place, just to suck all these gases out before the process is starting. That is possible. So I recommend this if you have really massive solder areas. So we have solder joints like that for some power modules, or we see an application later on ceramic dies, etc. There it can be really good to have a pre-vacuum. After the soldering, we can add an additional one. So we can add 2 vacuum steps. It's also recommended if you see, okay, I have a certain void ratio and I could reduce it up to 10% after the first one, and I want to go really below 1%, then I would have to add another side vacuum cycle. And then you can really come down to lower than 1%. Just a short overview how the void reduction in the vacuum is looking like. So the basis is we have the liquid solder and we have a void which is there. And then we apply the vacuum, so we are reducing the ambient pressure, and what is happening? The void is increasing. The void is increasing and increasing as long as we lower the pressure inside the vacuum chamber, until the void can build such a channel, because this channel is necessary that the void can degas out of the solder joint. That is what we want to achieve. So coming back, what I said, if you have a really big solder joint, it could be that the first vacuum step is not enough to bring or to make this degassing channel. And that is the reason why I said then you can add another vacuum step to really achieve, to reduce the void ratio in the bigger solder joints. The final pressure is around 0.1, 0.15, and then the void will be degassed. And now the good thing is, after we applied the vacuum and we have the final pressure, the void will shrink again, because we have the normal pressure in the atmosphere after the vacuum took place. So we are coming from this void to really this void. And this is how the vacuum treatment is looking like. Actually in every reflow machine, but particular in the Asscon machines. And then we are good and had the reduction. I just skipped this movie because it's just showing the process again, but it's quite long and I cannot go forward. So actually it's just showing the same principle that you see it live from a movie from a machine where the void rate is reduced. Why is vacuum so important for the future? I said it at the beginning. Automotive is requesting, and I'm in close discussion with such automotive companies in Germany, the overall requirement is below 10% in terms of void rate. Below 10% is something which is really not achievable without vacuum. And that is the reason why, so power applications is even more, but this is really, or this behavior and this requirement lead to the factor that vacuum will be much more important for the future. So for companies who are working closely together with the automotive sector, I think at some point you should think about to add the vacuum capability to your factory. Vacuum can also improve the solder joint strength. That is out of the question, we saw it. If you don't have voids inside, then of course the mechanical stability will be better. Here is just, it is really a basic calculation. So it's a basic calculation. If you have a MOSFET with a continuous current of 10 ampere and you have a 30% void ratio, then at the end what you can really get out of that MOSFET when you place it on a product, if you have if you have one MOSFET with 10 ampere, you would have 7 ampere due to the void rate. Just you're losing 30%, that is clear. With a safety factor of an additional 15%, then you get from 10 ampere 4.67 ampere out of that. That is just a simple calculation. And if you would produce this vacuum and reduce the void ratio to 3%, then you see the calculation. You have not 7 ampere, you have 9.7 ampere. Calculating with the safety factor, you have nearly 2 ampere more just by using the vacuum. And what does this mean? You have more continuous current, but the factor, and this is for the designer the important thing, you don't need the same power, so you need less parts, so you save money, and you can design the products a little bit smaller because you don't need the space on the products to add, instead of 10 MOSFETs, only maybe 8. So you can really reduce the costs for the products. So the vacuum is really helping you. So, summary. It is an additional process to improve the solder joint quality in terms of void reduction. So we have a higher mechanical stability, we have a better heat dissipation, we have less interferences on signals, but when you think about high frequency applications. Important, it has an increased lifetime, so if you want to produce a satellite control unit or something, then you have to make sure that this is not fall out after 2 years, so it should be at least 25 years. What I said, reduced numbers of components and space requirements. And this is all important for the production for tomorrow. And now I have just some applications, I think I have the time for it, that's good, some real applications which we fulfilled for our customers. What you can see, what vacuum technology or vapor phase technology is capable. So here really the challenge was to solder these 3 portions all together in one process. So we have a metallic plate, we have a ceramic die, and we have those components here on top. And the customer challenged us to really solder this whole part in one soldering cycle. So when you see this to profile in a convection oven, it's really difficult. And here really vapor phase is helping, because here we are just using the behavior that we have this equal temperature, no overheating possible, and we can place the assembly as it is in the vapor phase oven. And we can keep the delta T, which is also a requirement, as low as possible. So the result was that we could achieve the delta T below 1%, and we could reduce with the multi-vacuum technology the void ratio down to lower than 1%. That was achieved. And the customer, I think now it's the 5th or the 6th machine they already ordered. Here, also application, it's a power module on ceramics with open copper. So the challenge was here to solder it, to get a minimum void ratio, and the customer has a variety, and the customer didn't want to bring too much engineering in the profiling. So actually the requirement was to solder that with one profile. That was the task. So at the end, here's the result. Also here, we could solder it without no problem. As we have here open copper surfaces, we equipped the machine with a nitrogen atmosphere in the cooling zone, because the customer has a post-processing, and here oxidation is really an issue, so we added nitrogen here. And this customer can now produce these parts with 2 profiles, and the only thing why they have to use 2 profiles is we have the width adjustment in our inline systems. So the only thing what he has to do is changing the profile, because the width is a bit different, but actually it's the same profile. So also here we could really fulfill all the requirements the customer had on this stage. And because I said, some people say vapor phase is a bit slower than convection, and this is also not in every case correct, because here we have a cycle time of 15 seconds per ceramic. That means for each individual part it's below 1 second. So now you can judge if it's slow or not. And then coming to the picture which I had at the beginning of my presentation. What should I say? It's a component. It's a product which has a variety of different components on the assembly itself. I think it could be possible to profile it on a convection oven, but you have to do a lot of test runs to achieve it. On a vapor phase system, actually you could place it just as it is, take a really conservative profile, and you would get quality soldering afterwards. And then you can really fine-tune the profile if I need certain safety, so I would take it a little bit longer into the vapor, or if I want to improve my cycle time, then I would reduce the post-heating time and really look into that everything is soldered afterwards. So here really fine-tuning is an aspect. It's not a challenge for the Vapour Phase machine to solder that. Yeah, and also see, coming to the result, we could solder it easily, and also here the delta T at the end of the process was below 1 degree, even with this high variety of different components on the product. Yeah, this is actually what I wanted to present, and as you can read it, it is really soldering the simple way. Thank you.